Okay. So we finished the multiplexer, right? Now our intention is gonna be in the reverse of the multiplexer, which is called what? DEmux. But before we go to the DEmux, I have to build circuits using multiplexer. So it will make more sense for us, why we are studying multiplexer, right? So imagine the following. Somebody told you that, I have here a box, and this box has 1, 2, 3 inputs. And this input is what? A, B, C. Each one is 1 bit representation. Then the output of this box is just like 1 wire, which is 1 bit also representation. What is exactly this box is doing is actually called majority encoder. It's called majority active high encoder. What does this mean? It means the following. This box, it will look to all the wires and it will see if it finds the majority of the inputs are ones, then the output will be 1. If the majority of the, other than that, it will be 0. Okay? We need to build this using multiplexers. So that's called what? Design a majority encoder using what? Multiplexer. When we say design, that means we have to start from what? The step number 1. What is step number 1?
Derive expression.
Perfect. So first of all, we're gonna go and we will make first the twist table. On the twist table will be what? A, B, C. We have 3 of them, right? So that means how many states we have? 8 states. 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. Sounds good? Okay. Now I need the output. Let's call it OB. So we know that we're gonna look to the design state by state, right? And see if it's majority or not. That makes sense? So now those are 3 zeros. Is there any majority of 1 0? No, so it's gonna be 0. I have just 1 in front of 2 zeros. So who is winner?
0.
0. Same thing here. Now I came into the point that 2 1s versus 1 0. So who is the winner? 1. Then here is still 0. Here is 1. Here is 1. Here is 1. So far, so good? Do you guys agree with me?
Mm-hmm.
Okay. Now we need to build this gentleman using what? Multiplex.
Multiplexer.
Okay. What type of multiplexer we should have? It can be it can be 8x1. Do you want to see?
I'd like to see 8x1.
So look. 1, 2, 3, 4, 5, 6, 7, 8.
Can we use a 3 multiplexer of the 4x1?
You can do many things. I'm gonna show you 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. And then we have here what selector gonna be 3-bit selector, and OB will be here. Guess who will be the selector in this case?
AB.
ABC. It's a 3-bit.
Oh, yeah, it's 3-bit.
It's gonna be ABC. So when ABC equals 0, 0, that wire would be connected, right? So we can go back to our table and see in that case, it should be connected to 0, 0, 0, 0, 1, 0, 1, 2, 1. So what in front of you, I built a 8x1 multiplexer, which is performing 3 inputs majority encoder. What do you think? Sounds interesting? Let's be a little bit tricky. Let's make it with 4x1. So let's go in a 4x1. 1, 2, 3, 4. 0, 1, 2, 3. And then, you know, I have here how many bits? Two bits. And I have here the OB. So I can look to my table and I can come and say, you know what? Interesting. I can say I will take B and C to be the controller. Okay? So I can take B and C and I make them a controller. Right? Then I will start look to what different aspects here, 0, 1, 2, 3, whatever, right? So let's see how this is gonna work. Let's be tricky, right? B, C is equal 0, 0 how many times?
4 times.
2 times.
Perfect. But in both cases, the output is what?
0.
So in that case, we can just connect this to the ground. Do you agree?
Yes.
Professor, are we using both of these multiplexers together?
No. This is configuration. This is another configuration.
Gotcha. Okay, thanks.
Okay, look. Anyway, let's move forward. So now we need to see when it will be 0, 1. So 0, 1 happened twice here, right? Do you agree? 0, 1. The output is 0. Look at this. When is A is what?
Oh, it follows A.
0. And here the output is 1 when is A is 1. So pretty much we can come and say this is connected to A.
Yeah.
Sounds interesting, right? Now let's go to the third option. 1, 0 and 1, 0. So the output is 0 while it's 0. And here is 1, what is 1? So still it's gonna be connected to A. Then the fourth option, 1, the output is 1 while I'm in 0, and the output is 1 while it's still 1. So that means I don't care about A, I just connect it to 1. So this circuit is performing what? Performing majority encoder 3 variable input. That makes sense? Give me 1 second, please. So are you guys following what I said? Hello?
Yeah, it
Yes.
makes sense, Professor.
Yeah.
Just 1 second. So, you know, you can imagine that, you know, you can do it with multiple ways, other ways. Right? One second. I'm just connecting something. Okay, so now we're gonna move into the other circuits. What circuits we can have? Do you remember the adder? We can build 1 bit full adder using the multiplexers. Why not? Right? Let's do it together. So now we know somebody's telling you build for me 1-bit full adder using multiplexer. This question can be a little bit tricky because I can say, for instance, use a bunch of 2x1 multiplexers to build 4x1 multiplexer. So that means you're gonna do whatever we have done in the first lecture about multiplexer last time, plus whatever I'm doing now, right? So if somebody telling you 1-bit full adder, that remind you with a circuit, it has carry in, and it has 2 operand, which is A and B, and the output will be sum, and the other output will be carry out, and that's called full adder. Do you guys agree with me? Do you remember this one or not? How many remember that?
Yes, I do.
Okay. If you don't remember,
Oh yeah, it's crystal in my mind right now. Promise.
So now, same trick. We're gonna go and make a table and say A, B, C, I, N. Those are the 3 inputs we have. How many outputs we have? We have sum. We have a carry out. That means 2 outputs, right? 3 input variables. So that means how many state? 1, 2, 3, 4, 5, 6, 7, 8. E1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. Then we're gonna do the summation. Do you agree about that? So we're gonna do it per state. So here we're gonna be 0, 0. Here we're gonna be 1, 0. Here we're gonna be 1, 0. Here we're gonna be 1 plus 1 is what?
0.
You have a carry out. Here is 1, 0. Here we're gonna be what? This state.
0. And then carry out is 1.
Now somebody else tell me, what is this gonna be? Joseph? Joseph?
I'm sorry.
You're fine.
Yeah, I left for 2 seconds. I'm so sorry. I was gonna fill in the table when I got back.
Oh. Okay, so tell me, what about this one? What is sum in this, and what is the carry out in this?
Sum is 1. No, sum is 0.
Okay.
Carry out is 1.
Okay, Gloria, what is this one? Huh? Gloria. Yeah, I hear you now. Tell me.
Okay, sorry. Sum is 1, carry out is 1.
Okay, perfect. So now, we did the most important part of this question. We build a truth table, right? Then we will go and say, Professor Ali said build it with multiplexer, but he didn't say what size of multiplexer, right? It can be any size of multiplexer, right? Let's say that, I am, as an examiner, I told you build it with 4x1. First of all, how many multiplexer do we need for building this as a 4x1?
3.
We need 3 to build the 4x1 from 2x1. You're right. But how many of those 4x1 we need? 2. Why? 1 4x1 for the sum, 1 4x1 for the count. See how? That makes sense? Why?
That's gonna be clear when you do the rest of the question.
I will do it.
I agree.
Yeah, exactly. I need to do for the question. Exactly. So I will, the trick of how to build it using small multiplexer. So I'm not going to throw it again. So I'm going to say that, I need a 4x1 like this. And there 1, 2, 3, 1, 2, 3, 4. And then my selector here. And then, they're going to be the sum. And I need another multiplexer also for the carry out, because every single output, it will have its own multiplexer. And then it's going to be here 1, 2, 3, 4, 0, 1, 2, 3, and then it's going to also have here a selector. And here going to be carry out. Then we'll start looking at, right? those are 4. So maybe I can take AB to be the selector. Let's be more tricky and make it AB selector. Let's see what will happen, right? We believe that, this truth table is like a Lego for us, right? Or the Play-Doh. You just like do like this, whatever, it will work. So here, we're going to say it's AB, and here going to be also AB. Maybe I can make this one AB, and I make this one something else. Do you agree? Let's go in here in AB. Okay. So AB is equal 0 in this location. AB is equal 0 in this location. Is there any other location in the table AB is equal 0?
No.
Who is the third input?
So in this case, it's CN.
Exactly.
Okay.
Because the
Okay.
sum here 0, 0, and here 1, 1. So CN. There, no matter what, it's gonna be 0. So it's gonna be here, ground. Look, it's 0 when CN is equal 0. It's 0 when CN is equal 1. So there is no relation, right? Now we're gonna look to that 0, 1. So maybe we need to ask Jeremy. Jeremy, can you reply to me about what will be the input in this case for the sum?
I'm sorry, I'm having some connection issues. Can you repeat that?
Okay, we covered this part, right? When the AB is equal 0, 0, right?
Yes.
Now the AB is equal 0, 1. How many 0, 1 we have in this table for the AB?
Oh, we have 2.
Right, those, right?
Yes.
So we need to know what is the functionality of the
of CN. Okay.
So tell
When it's basically the opposite of CN,
so
right?
that
For
means CN what?
CN
Complement.
complement. Thank you.
Yes. What about the C out? What it will be?
It'll just be CN.
Is Jeremy's correct?
Yes.
For sure.
Yes.
For sure.
I agree.
I don't understand C in complement. It's because I would think C in complement is 1, 1, 1, 1. Why would it be 0, 1, 0, 1?
Let me tell you something.
Okay.
CN, it's a wire, right? It can
Yes.
hold 0 or 1. You agree?
Yes.
So look, when CN is equal 0, the sum is equal 1.
Oh, okay. We're looking at that. Okay.
Exactly. When is the CN is equal 1, the sum is equal 0. So what is the relation between of them?
Yeah. It's
What is the
complement.
complement of the CN?
Okay.
That
All
makes
right
sense?
then. Yeah, it makes sense.
Okay. So now we need somebody to Jamal. Can you go ahead and tell me what is the 1, 0? This 2.
So for sum, it's going to be CN complement for
And for the other one,
for C out is just CN.
is he correct?
Yes.
Okay. Now we need Austin. Austin,
Hello.
yes, tell me, what about 1, 1?
1, 1, it would be for the sum, it would be
Hmm.
CN.
CN, okay.
And then for the C out, it would just connect to the battery, right?
Yes. Is it correct, guys?
Yes, he's correct.
So now it should be clear, right? Is it fun?
So we can use gates now.
Yeah. You don't need, did you see any gates? Of course, if you need to make gates, you can use here something for the CN complement, right? You can use NAND gate. How can you make a NOT gate from NAND gate? Somebody remind me.
So basically, you just take both inputs into a 2-input NAND gate
You mean like that?
for a NOT gate, right?
Yeah, is it correct?
Short the inputs.
Yeah.
Daniel, do you think it's correct? Daniel? What about Christopher? The two Christopher, what do you think? Is Juan is correct about this? Is this equivalent to this one? Think so. Okay, it is correct. Yes. So I have another idea, which is also combinational circuit, you know? Look at this. Have you ever seen the 7-segment display? 7-segment display, by the way, is an encoder. It's a kind of decoding. I'm sorry. Right? What is the 7-segment display is presenting from your point of view?
Sorry, can you repeat that?
7-segment display, do you know?
I use it with Arduino.
So here's 7-seg display. In 2300, you go by decoder for it, right? And you connect the decoder to the 7-segment display, then it's voila, it will just represent the stuff. Can you build the decoder?
Yeah.
It's an easy peasy lemon squeezy. You know why? I will tell you why. Digit. Like this is a digit, right? If it's presenting 0 to 9, we need how many bits?
9.
5. Oh,
There's
4?
no-
Not 5. 4.
4. Not that.
This guy can present 0 to 9, right? That's like, you know, in the decimal, right?
Yeah.
In the hexa, it presents 0 to F. Right? So still we need 4, right? So that means if I want to build the decoder, so I expect the decoder will be like this: 4 inputs and how many output? I will show you how many output: A, B, C, D, E, F, G. Every single LED, it's a segment. You got it? So now we're gonna be A, B, C, D, E, F. And this what you have to do when you're buying it from Micro Center or from Fry's or whatever, right? So how are you gonna build it? You can build it, right? It's not that really hard. I can tell you how can you build it based on our lovely truth table, right? Those guys are switches, right? So those guys can be A, B, C, D. How many input variables do we have?
4. Wait, hold on. No.
How many input variables do we have?
4 bits.
4.
4. A, B, C, D. That means how many states we have?
16.
16, that's correct. So it's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? We're gonna make it here 0, 1, 0, 1, 2, 1, 1, 2, 3, 4. 1, 2, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. You agree? Now, how many outputs we have? We said A, B, C, D, whatever, right? So it's gonna be here A, B, C, T, A, F, G. Right? Gonna be here A, B, C, D, E, F, G. Right? So that means how many outputs we have? 1, 2, 3, 4, 5, 6, 7. We have 7. And sometime you find like a dot like this, right? Decimal point there, right? You can add it if you want to be an extra output. That's why. Okay. Now we need to what? To draw characters. We draw numbers on it, right? So let's see what numbers we can draw. What numbers we have in the digit? We have 0 to whatever, right? So we need to draw 0. And when the switches are tied to 0, 0, 0, that means I should see on the 7 segment display 0, right? So in that case, I will go in my 7 segment and draw 0. This is 0, right? So that means A, B, C, D, E, F, all of them are 1. And G is 0. So I can just write here 1, 1, 1, 1, 1, 1, 0. That makes sense? If it's active high, because if you look in the 2300 lab, you will find some of the companies send you 7 segment display with common anode and some of them with common cathode. Do you remember that?
Yes.
So that means with common anode, that means the ground is anode and every single segment is it's active with 0. And it's common cathode the reverse. Make sense? Okay. Now, what is the number we need to write after 0? 1. So BC is basically equal 1 and the rest is 0, right? B and C1 and the rest of them 0. Then what is the second number we insert in the row? Gonna be like this. What is this? 2, right? So that means A and B and D and E and G are 1, right? So gonna be A, B, and D, and E, and G are 1, and those are 0, right? What is the one after this? It's gonna be 3. 1, 2, like this. So that means F and E are 0, right? F and E are 0. F and E are 0. Then 4, for instance, 4 like this, right? So in that case, who is not exist? E and D and A. E and D and A. E and D and A. Then you will move forward to the rest. I'm not gonna continue this, just giving you the idea. You know what I mean? Then I can come into the exam and say, you know what, build it using the K-map. I mean, just build it with gates. That's called gate level implementation, right? So you're gonna take every single output, you make a K-map for it, and then you will make the Boolean algebra, and then you will use the gate equivalency, and you will.
Wait, Professor, can't you not go above a certain number though?
Like?
Number, like, can't you not go above 9? 1001?
You can, you want 9? Okay, 9.
No. Like you can do 9, but I thought you can't go above it. Like
you can
can't
go, of course. If it's up to you. Do you want the decoder to be BCD decoder? That's called BCD, by the way. If you remember the BCD when we were talking about, right?
Yeah.
The BCD decoder goes 0 to 9. Anything
Yeah.
it go above 9. What is above 9? A. How can you write A in this place? A like this. That's an A.
Okay, makes sense. Thank you.
If you want to write D. If you want to write E. If you want to write F. And so on. So now, that makes sense?
Yeah, it makes sense. Thank you.
You're welcome. Now, I can also ask you to build it with multiplexer. Do you guys agree? Same thing. I can tell you, oh, go build this in multiplexer. How many multiplexer we will need for per output? It's gonna be 1 to 7 outputs, 7 multiplexers, or 7 multiplexer system, right? And each one it can be built from whatever combination I want. Is it clear?
Clear.
Okay, that's also combination circuit. You know what we're doing now is combination circuit. So all of this is under the combination circuits. We are learning a lot now. Okay, now if somebody tell you, can you build for me 2-bit comparator? 2-bit comparator. We did that before. Do you remember? We did it with gate level implementation. I remember that. So how does 2-bit comparator look like? 2-bit comparator is like this. Right? Here is a 2-bit comparator, A and B. When I say 2 bits, that means every single input is represented in 2 bits. So that means this is 2 bits and this is 2 bits. What outputs we can get out of this comparator would be 3 possible outputs, right? Which is basically A are equal to B, or A greater than B, or A less than B. Make sense? But then the truth table would be built based on what? Based on number of bits as input, right? So this is 2 and this is 2. So that means end of the day gonna be what? 4.
16.
16 states, exactly. So 3 outputs, which is gonna be E and G and L, but 4 inputs, which are gonna be 16. And you will do the same thing. You start comparing between values. Like here, I can make it for you. It's not really hard. You're gonna be here B1, B0, A1, A0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 0, 0, 0. Ah, 0, 0, 0. That was the first segment, right? And then you will move to the second. 0, 0, 1, 0, 0, 1, 1, 1. You're gonna be 1, 0, 1, 0, 1, 0, 1, 0. Then you move forward. 0, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. Then you're gonna go into the last part. We're gonna be what? 0, 0, 1, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Correct? Now we're gonna write here GLE, and we are looking for the correlation and relation between these, right? So I'm looking as a comparator, so I'm looking for A as a value, right? So this A value and this B is a value, and I'm comparing between of them, right? So this is 0, 0, and this 0, 0. That means I'm comparing 0 to 0, right? So in that case, I'm gonna write here 1 and 2 zeros, right? Then A is 1, but B is 0. So what is the output will be? Great. Then A is 2, B is 0. So the output is what? It's still great.
Also great.
Then same thing, greater. Then the same thing, right? This is less. This is equal. And then this is greater. Greater. And then this is also greater. Then you understand what I'm doing. Everybody understand what I'm doing, right? So like this is 0 and this is 2. That's gonna be less. 1 and 2 is still less. Then 2 and 2 gonna be equal. Then now 3 gonna be 1. Then same thing here, right? So gonna be 0, gonna be less, 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 equal. Then I can ask you for anything. I can ask you for gate level implementation. That means you're gonna make K-map and you optimize and use gates and you implement. Or I can ask you go ahead and build it with what? with multiplexer. And still you can perform it with multiplexer as you can see. So my question, is it now quite clear?
Professor, can you explain what we're comparing again? Like we're comparing A to B, correct? And we're just trying to find out who's lower or greater?
Look, A is 0, 0, right? B is 0, 0. So what does it mean?
That they're equal, correct?
And when I say like this, bit, 2 bits. So I do decimal in my head, right? So this A 0, 0, that means 2 power 0 times 0 plus 2 power 1 times 0 is 0, right? So the value of A is equal 0, the value of B is equal 0. That means they are equal. That means the other two are not exist. They're not less, they're not greater, right? There, this one is 0, 1. That means it's 1 in decimal, right? Versus 0 in the other side. So basically, I'm comparing 1 to 0. So I said, if it's A greater than B, so that means G will be equal 1. Do you understand what I'm saying?
That's all I needed to see, that inequality. Thank you. Wait, actually, could we also do A is less than B if we wanted to?
You can add extra line, extra output.
Okay,
That makes sense?
gotcha.
Any other questions so far? Sounds good?
Yeah.
Yep.
Now we're gonna move to Captain DEmux. What does it mean, DEmux? Is DEmux. The other guy was called Mux. Right?
Yep.
This guy was NX1. This guy 1XN. Okay? This guy was like, like this. That guy is like this. This guy selector is based on the number of inputs log 2. This guy selector is the log 2 number of outputs. That makes sense? Okay. So, example. This is input, and this is output 0. This is an output 1, and that's 0, 1. Right? And here is my selector. So what is the size of the selector will be?
1 bit.
1 bit. Let's make a table out of it. So the table would be the following. Selector, output 0, output 1. Right? If select is equal 0, so that means output 1, it can be 0, but output 0, it will be input. Right? If select is equal 1, output 0, it maybe can be 0, and they're going to be input. So far, so good. So we can write a very nice equation saying input, output 0 is equivalent to select complement input, while output 1 is the select with input. That makes sense? How to build a circuit with this? It's an easy peasy lemon squeezy, right? Look at him. Sorry. right? Have you noticed something? This circuit, it almost looks the same like the multiplexer, except the multiplexer just have an OR gate in the top of that. You guys agree? Any questions so far? If you have any question, don't hesitate. I'm here to help. Somebody will say, hey, Professor Ali, but we need to see also inputs should be input in the twist table and the output should be output. We're gonna do the same thing, no problem, right? So we have here, we have select and we have input 0. And we have how many output? We have output 0, output 1. So since the select is and the input 0 are 2 variables, so that means how many steps we should have? 4. So 1, 2, 3, 4. 0, 1, 0, 1, 0, 0, 1, 1. Right? We said if select equals 0, what will happen? Huh? The output will be the output, right? So basically, if select is equal 0, so the input 0 will be the output 0, right? So gonna be here 0. But that guy will be 0. If select is equal 1, so whatever input will be the output, right? So this one here, input here, and still the gap is 0. If select is equal 0, that will be what? The inputs. The input in this case is 1, and that guy is 0. If select is equal what? 1, then that guy would go here and they're gonna be 0. Right? Then let's look at it. You will find just one term, you don't need even came up with anything, right? So in that case, write it down. So you're gonna say output 0 is equivalent to select complement with the input, and the output 1 is equivalent to select ended with the input. And what we are doing now is this min term for both of them. If you look at this equation, you'll find it the same like in the one and the above. Make sense?
Yeah.
Now, we need to build a network of demultiplexers. If we have a small number of multiplexers, I'm in the lab and I'm in the middle of a great experiment, and I'm listening to Beethoven, I'm doing a lot of crazy stuff, and then I don't have the IC which has a bigger demultiplexer set. What should I do? I'm gonna pause and go take my car, buy the stuff, and come back, or I will just use whatever I have. Use whatever I have. If I want to build 1x4 demultiplexers out of bunch of the 1x2 demultiplexer, what I'm gonna do? Easy peasy lemon squeeze, right? Here. The select will be the same select, right? Output 0, output 1, output 2, output 3. Right? Do you guys agree? Same thing we did before with multiplexer. In that case, how many bits we will need to control for output? 2 inputs, 2 input bits, 2 input control. If you look at the normal demultiplexer, if you have it already 4, it's gonna be like this. So that's the same like this. Any question? Interesting. Now, We finished the demultiplexer, and it's almost multiplexer but flipped, right? We can build a circuit using demultiplexer, right? We already built with multiplexer, so why we don't build with demultiplexer? That's not fair, right? How are we gonna do it? Somebody tell me. Let's have a target, right? 1 bit full add. We need to build it with demultiplexer. Let's see how it's gonna look like, right? So let's make it half adder. Do you know what is half adder, right? How many of you are aware of half adder? I mentioned that before. So half adder, the first digit when we are actually adding, right? You don't have a carry in. So it's basically like this. A added to B, and there's some, and there's a carry out. There is no any carry in coming from the previous stage. So you don't need this anymore. So that's called half add. Sounds good? How can we do this? Physically is very easy, right? I have here A and B, and they're gonna be 1, 2, 3, 4, and 2 some here, and carry out there. Then I would say 0, 1, 0, 1, 0, 0, 1, 1. Here gonna be 0, 0, here gonna be 1, 0, 0, 1, 0, here gonna be 0, 1. If somebody tell you, I want to build this circuit using demultiplexer, so what would be the solution then? Somebody tell me.
Sorry, could you repeat that? You cut off.
I want to build this using demultiplexer. What should I do? They will tell you build it with demultiplexer with associated data. Tell you.
Should we inverse all the values and then make a demultiplexer?
So we have 2 outputs. Does that mean we're gonna use 2?
Two of them, yes, 2 demultiplexer, yes. Somebody tell me, please. Just think about it, you know.
2, 2, 1, 2, 4.
Like this?
Yeah, and
Let's play and see how it's gonna work, right? So 0, 0, 1, 0, 0, 1, 1, 1. And that will be for sum, right? Do you agree?
Mhm.
So when it's 0, 0, I want my output to be what? 0, right?
Yes.
So let's see how we're gonna do it. Uh-oh. If we do like this, so we need this input to be equal what?
0. Ground.
We need it to be 0, right? Interesting. You know what? We can put 1 here. Okay? Then we do like this. Right?
Yeah.
We tricked the system. Yay. Okay, now, you know, let's go in the second one. It has to be 1. Take 1. It has to be 1. Take 1. It has to be like this. Then take all of this, put it in OR gate, and you got some. right? Are you guys are following me?
Yes.
Sounds good, right?
So can I ask a question?
Yes.
So for the input, do we have to put a 0 or a 1, or in this case, could it also be like another variable, like a C maybe possible?
We can try to make it a function from AB. What do you think? Do you guys agree with me? Like I can tell you something now more fun. You know? I love fun stuff. Don't worry about those. Those are bad, ugly.
Explain the. Could you explain this
This one again?
Explain the demultiplexer.
This one, right? The demultiplexer? Tell me what?
Because I can understand how to do it with like logic level gates, like with NAND or XOR, but like I can't. I don't know, for some reason it's a little bit.
I'll tell you. AB is 0 and 1 and 2 and 3, right? If it's 0, 0, that means the input will be the output. Do you agree? So that means this wire will be holding whatever here. Like, Juan was saying, let's call it I, right? So if it's 0, 0, that means, I0 gonna be equal I, right? But then, if it's 0, 1, that means, 1 will be I. If it's 2, it's gonna be 2 will be I. If it's 3, 3 will be I. That makes sense? Okay. Now, what we can do, instead of building the circuit after the output, we can do something even more fun. You know what? We can go ahead and say, sum and A and B look like something really interesting, which is what? XOR. This one is an XOR. Do you agree with me?
I understand.
Yeah. So now what we can do, we can take A and B like this, XOR, and then we connect it to the inputs.
And then we just add A and B.
Exactly. Then 0, 0, it will go here to be 0, and the output will be 0. Then put here 0, 1, it's gonna be 1, and then the 1 will be written here. And then gonna be 1, it's gonna be 0. Then you're gonna go here with fancy OR gate, and you're done.
Can I know why we added the?
Okay.
Huh?
Why did we added the gate?
Which gate? Which gate?
The
One
last one.
gate with the demultiplex, it cannot be built by itself.
So we add a XOR gate for the
with associated
select.
Gates. Build it with demultiplexer with associated gates. When I say with associated gates, that means you can build with any gates. Or I can trick you with demanding, say that I want this gate, specific gate, like I did now. I already made a trick, right? Let's build the carry out. Let's build the carry out, carry out. Yeah. Zero, 1, 2, 3. Carry out is just one output wire, right? So I need wire. So basically, I just need an OR gate like this, go in here, right? Now I need A and B, A and B, right? I know from this, that means the only one give me 1 in carry out when A and B are equal 1, right? Do you agree? So what I can do, I can take cable from here, cable from there, and put them in what? AND gate, and I pass it like this, right? Then we are done. Let's try, right? Put here A and B equal 0, 0, right? So 0, 0 will go here. The output here will be 0. But then this A and B selected this position to be what? To be the outputs, the inputs. So they're going to be here 0. 0, and I have no idea what it's going to be here 0. Then, let's go to the other one. The A and B is going to be 0 and 1. So that's still also 0, 0. Then 1 and 0, they're gonna be 0, 0. The only one is gonna give me 1 when this is equal 1, 1, so it's gonna be here 1.
Okay, I get it now.
So Professor,
for the outputs.
Huh?
So the input that's being demultiplexed is the same as They can be derived from the same select input.
It's just extending wire. Nobody can stop you from extending wire from point to point, right?
Suppose not.
We are not using gates, we are using wires. We have a lot of wires with Mark. Sounds good? We can be a little bit more tricky, by the way. If you want me to be more tricky, I can tell you.
Yes.
I can tell you trick. Wait, here. Look at here. This one is what?
Which one?
This one is a demultiplexer, right?
Yeah.
Do you agree, right? So basically, I can actually connect OB1 with this part, and I kill this part completely. And then, I will just use another demultiplexer to be input here to perform this end.
Oh, I see what you. Oh, I see now.
Makes sense.
Okay,
Let's build it. That's pretty fun. Anyway, look, you can have here a multiplexer like this, 0, 1. Wait. Gonna go here. 0, 1, 2, 3, and like this, and then no, be more organized, Muhammad. So it's gonna be different. It's gonna be like this. Right? And then this is floating. I don't care about it. Okay, so now this one will go in OR gate, and this one can be as follows, right? It's a demultiplexer. I can connect this by 1, and then I have 2 wires, right? Those 2 wires gonna be. I need to activate that part, but I don't need this part, right? So I need this one of the selector to be equal 1, right? So I can just correct it like this to be selected equal 1. And what? Wait. Let's see this one. If select is equal 1, the input would be equal 1. So you can put here also 1. And then no, it will be a little bit tricky. We have to add more gates. You understand what I'm saying? You know what I'm doing, right? The rest of the people are following me. You know what I'm trying to do, right? I'm trying to completely just use decoder, demultiplexer. That makes sense?
So we need more gates. More gates, right?
Yeah, we need more gates to play with this. It shouldn't be that much hard, but I mean, just a trick. Because you don't need this anymore, right? And you already have here A and B. 0, 0, 1, 0. Like this, right? When is 0, 0? And when this one to be 0, right? And then I want this to be 1, and I want this to be 1, and I want it to be 0, right? Okay. No. That would be too much. It will be a bigger circuit. You know what I mean?
Yeah, I think you're adding more gates.
It will be more gates. No. I'm not gonna put too much stress on this. So at least you understand the trick, right? You can build it with multiplexer and demultiplexer. Do you think it can happen?
Yeah.
How? If somebody tell you build one bit half adder using multiplexer and demultiplexer, what are you gonna do? You want me to show it to you?
Yeah.
That's it. Right?
What would a full adder look like?
Huh?
What would the full adder look like in this equivalent?
Same trick.
Okay.
That's something you need to do by your hand. You know, I'm not gonna say, I'm not gonna do everything, right? Anyway, any questions so far?
Yeah, Professor, I do have a question. So is an encoder the AOI equivalent of a multiplexer?
What again?
Is like an encoder like the NAND equivalent of a multiplexer?
No. You
Or
can,
they're separate?
yeah, you can build a multiplexer using NAND gates, of course.
But an encoder is like a separate entity on its own?
Nah, what do you mean?
Oh, I'm just wondering if they like do similar functions, but they're constructed differently.
When you build it with gates, it's called gate level implementation. When you build it with components, it's called combinational circuit.
Okay.
You know what I mean? So if you can build it with gates. I already built it with gates, right? And I can build it with devices like multiplexer, demultiplexer, encoder, decoder, whatever. That makes sense? I just want you to be sure to understand my language while I'm writing the thing. That will be the whole trick. And you can see, I'm in front of you, I'm just playing, right? I'm just putting numbers and connecting stuff and testing whether that thing is already giving me whatever I'm looking for or not. It's a logic thing. Any questions? If there are any questions, please let me know before I go.
I do have one question, and it's similar, related. What are the relationship between a DEmux, multiplexer, and encoders and decoders? I know that Melvin asked, but I'm curious myself too. Like, what would distinguish one from the others?
Oh,
that's exactly what I want to know.
Multiplexer is basically like multiple wires, and you would like to go in one direction, right? Demultiplexer, one wire, you would like to distribute it to multiple points, right? That's used for routing. So when you are in the 2300 lab, you have too many wires, too much. So we are trying to decrease this amount of wire. That's why they have the multiplexer and demultiplexer. Encoder is encoder, I'm encoding. That means I'm moving from a level to another level to make it simpler and easy.
Okay, thank you. That helps a lot. Thank you.
Any other questions? So if no other questions, I would like to thank you guys for attending, and you guys actually have a very valuable questions that I really like. And I want to say that God bless you and stay safe. This is the most important thing, okay?
God bless you, Professor.
I'll see you on Monday, and then we will be working on what? We'll be working on the quiz, and in the weekend I will be trying to grade it so you guys can see your grade as well. Okay?
Perfect. Thank you, Professor.
Thank you. Have a good day. God bless you.
You have a good day. Bye-bye. God bless. Thank you.
Bless.